Continuing section 9.2 and looking at matrix multiplication, we now turn to the identity matrix. We saw earlier that there is a matrix that serves as the additive identity, and that's the zero matrix. There is also a matrix that serves as a multiplicative identity, and that's called the identity matrix. This is a matrix which, when you multiply it by a given matrix, it preserves that matrix. It doesn't change it. Just like the number 1 does not change a number when it multiplies that number. Let A be a matrix of order m by n. The square matrix In with the property that A times In equals A. By the way, sometimes we just write I and not with the subscript. The matrix In with the property that A times I equals A is called the identity matrix of order n. An identity matrix consists of entries of 1 along its main diagonal, that is from upper left to lower right, and entries of 0 elsewhere. For example, if you have a 1 by 1 identity matrix, that's just the number 1 in brackets. If you have a 2 by 2 identity matrix, then you have 1 0 0 1. So the main diagonal is what we call this diagonal here. If we have an order 3 identity matrix, I3, then we have 9 entries, 3 of which are 1, along the main diagonal, and all the other ones are 0. The type of identity matrix we use depends on what we're combining it with, what the order of the matrix is that we're combining it with, as will be demonstrated in the next example. Example 9 says, given A as shown, which is a 3 by 2, order 3 by 2 matrix, show that A times I2 equals A and I3 times A equals A. Okay, let's look at A times I2. A times I2 would be, and I'll just recopy A, 2, 0, 1, 3, 4, 2. I2 would be 1, 0, 0, 1. Now, what we're going to do is take a 3 by 2 times a 2 by 2. And you can see these inner numbers match, and the outer numbers are going to give us another 3 by 2 matrix. What we would expect that to be is the matrix A again. So we'd expect to have 6 entries, 3 rows, 2 columns. Let's see if that's the case. If we multiply row 1 with column 1, we would have 2 plus 0. Row 1 with column 2, 0 plus 0. Row 2 with column 1, 1 plus 0. Row 2 with column 2, 0 plus 3. Row 3 with column 1, 4 plus 0. Row 3 with column 2, 0 plus 2. That gives us 2, 0, 1, 3, 4, 2. In other words, it gives us A again, as we were hoping would be the case. All right, what if we do I3 times A? Here we're going to use the 3 by 3 identity. Multiplying that by A again, all right, the 3 by 3, of course, 3 rows, 3 columns. A has 3 rows and 2 columns. The inner numbers match. The outer numbers give us the size of the resulting matrix, the order of the resulting matrix, which should be the same as A, and indeed we get a 3 by 2. So again, let's fill in the blanks and see what we get. If we take row 1 of I times column 1 of A, we get 2 plus 0 plus 0. Row 1 with column 2, 0 plus 0 plus 0. Row 2 with column 1, 0 plus 1 plus 0. Row 2 with column 2, 0 plus 3 plus 0. Row 3 with column 1, 0 plus 0 plus 4. Row 3 with column 2, 0 plus 0 plus 2. Let's add 2, 0, 1, 3, 4, 2. Guess what? A again. What's interesting here is that if you want to multiply A by 1, so to speak, where the matrix playing the role of 1 is the identity matrix, the order that you multiply in will determine the type of identity matrix you need to use. And that's going to be determined by what being able to define the actual multiplication that will be performed. So because A is a 3 by 2 matrix, if you multiply A by I in front of A, then you have to have a 3 by 3 matrix so that the number of columns in I matches the number of rows in A. So it's, again, we see this peculiarity of matrix multiplication, and we have to be very cognizant of the order of the matrices and the order in which we do the multiplication. That makes a big difference when it comes to matrix multiplication. Now, using the definition of matrix multiplication, it can be shown that any system of linear equations can be expressed as a matrix equation. So let's demonstrate this with a linear system with two equations in two unknowns x and y. The a's and the b's would be specific numbers depending on the actual equations. So we have the system a11x plus a12y equals b1, a21x plus a22y equals b2. The a's and the b's being numbers, constants. Define matrices A, X, and B as follows. A consists of the coefficients on the left-hand side of the equal sign. A11, A12, A21, A22. Capital X represents what we'd call a column matrix consisting of the variables in the system, X and Y. B corresponds to another column consisting of the constants on the right-hand side of the equal sign, B1 and B2. If we define these matrices in this fashion, then it can be shown that the matrix equation AX equals B is equivalent to the original system of equations. Let me try to demonstrate that to you. If I take A times X, let me write them side by side as our custom has been. A11, A12, A21, A22 times X, that is X and Y. Okay, A is an order 2 by 2 matrix. X is an order 2 by 1 matrix. Notice the inner numbers match. The outer numbers will determine the order of the resulting product matrix, which would be 2 by 1, 2 rows and 1 column. Okay, what would the entries be? Well, there are only 2 entries, which would be generated from rows of A and the column of X, and doing a dot product. And that would be performed as A11X plus A12Y, and then using row 2 with column 1
a21x plus a22y. So that's a times x. If we set that equal to b, which is b1 and b2, what we have is a 2 by 1 matrix here and a 2 by 1 matrix here. Now, the one on the left looks like it has 4 entries, but actually it only has 2 because you're adding the entries in the first and second row. For those two matrices to be equal, it follows that their corresponding entries must be equal. In other words, this system of equations would have to hold. a11x plus a12y would have to equal b1, and a21x plus a22y would have to equal b2. So indeed, this matrix equation, ax equals b, is equivalent to the original system of equations shown above. So what this shows us is that a system of equations, a linear system of equations, can be written as a single equation, kind of like a simple linear equation, something like 2x equals 3, for example, except the a, the x, and the b are matrices in themselves and have numerous entries within them. The matrix A, by the way, is called the coefficient matrix of the system. So going to the next page, if the matrix equation ax equals b defines a system of linear equations, the matrix A is called the coefficient matrix of the system. The matrices x and b are referred to as column matrices because they consist of a single column of entries. Let's look at an example. We have two equations and three unknowns x, y, and z. For the linear system, x plus 2y minus z equals 0, and minus 2x plus z equals 1. Find matrices A, x, and b such that the system is equivalent to the matrix equation ax equals b. All right, so for this second equation, let's just note that there's a hidden y with a coefficient of 0. Minus 2x plus 0y plus z equals 1. And note that the coefficients are sometimes hidden from view. For example, in the first equation, there's a 1x and a minus 1z. So for the matrix of coefficients A, it should be a 2 by 3 matrix. 2 rows corresponding to the two equations, and 3 columns corresponding to the 3 variables. And we just write the coefficients of the left-hand side of each equation. 1, 2, negative 1, negative 2, 0, 1. That's the matrix, that's the coefficient matrix A. The matrix X would be a column matrix consisting of the variables within the system. In this case, there are 3 variables, so we'd have X, Y, and Z. Now, the matrix X would be like a capital X, and the variable X would be like a lowercase x. With my writing, you can't barely tell the difference, but that's the way it's supposed to be written. And then, what about the matrix B? Well, that would be a single column consisting of the entries to the right of the equal sign. That would be 0 and 1. Now, does it make sense to multiply the matrices and set them equal in this fashion? Well, it does if you write the orders. A is order 2 by 3. Capital X is order 3 by 1. B has order 2 by 1. So notice the inner numbers match here. The outer numbers determine the order of the result, which should be 2 by 1, which is exactly what B is. So the orders are consistent with the definition of matrix multiplication, and indeed this matrix equation AX equals B represents the original linear system given at the top, just above there. That concludes the notes for section 9.2. I'm glad you survived.